Hello, everybody. I know we have an international audience today. By a quick survey, I see quite a few people joining us from Russia and from other places in Europe. So hello to everyone over there. Good evening to you. And good afternoon to everybody on the East Coast. Good morning to everyone on the West Coast. I don't see any Japan so far, so nobody to say good night to. I would like to preface this by saying that my talk is going to be fairly technical, and it requires some knowledge of Python to get through. If you have problems with the technical content, stay tuned because there's going to be pretty pictures at the end, and the code is all presented in my book and in a number of other places as well. So you're going to be, if you miss anything, you're going to be able to first of all find it in the archives, and you'll be able to follow the code, follow up on the code later on. Also, the code has been uploaded to GitHub, and those of you that have programming ability and would like to follow along with me and play with the data live as we're speaking, I encourage you to go to my GitHub that you will see on the slides. Go to my GitHub account and clone the GitHub repository. It's quite large because I'm including a big data set. And this is the data set I'm going to use throughout the day for playing with the data and for working through all of our topics. So we're going to use this all along, and all of the code that you see in the presentation is also in there, and then some. So quite a bit of stuff to play with. Anyway, without further ado, actually, final preliminary is my book called Social Network Analysis for Startups. It is, as of today, probably one of the most accessible introductions into the field, into both the math and the practicalities of doing social network analysis. Today, it is actually, by an order of magnitude, the cheapest. And it is the deal of the day on O'Reilly website, and the ebook is only $9.99. So go grab yourself a copy, and you'll be able to follow along quite a few more other things as well. One of the questions that just came through is if that's okay to ask questions in Russian. Yes, but I will repeat your question in English to our English-speaking audience, and I will answer it in English. That is okay. So anyway, why do we concentrate on Twitter? Besides the obvious thing that it's trendy and everybody else does it. Twitter is rapidly becoming what I call a ubiquitous common carrier. It is not, I would say, it's not a social network in itself. It's not like Facebook. It doesn't so much capture existing social relationships or build social relationships as it acts for a carrier for other things to traverse it, for other information. So, in fact, Twitter is rapidly becoming almost like the old-style phone system or like the old-style radio networks, where information travels through the ether, and we are either there to capture it or we are not there to capture it. And I would like to talk to you about how to capture it and how to make sense about it. One of the beautiful things about Twitter is how fast it is. Any kind of global event find reaction on Twitter within seconds. And if the events are worth following, they get huge reactions. They go viral. The event we're going to use today for the example is an earthquake on the East Coast of the United States that happened in August. Sort of to tell you how crazy I am. Everybody was running down the stairs and trying to get out of the buildings while the earthquake was happening. I was starting my Twitter collector. So I have a data stream that is fairly up to date. It's not seconds after the earthquake, it's minutes, but it is there, and I have pretty good data set. So if those of you that have cloned the data set, that have cloned the GitHub, will now have this file sitting on your machine. It's a JSON file. And we'll use this JSON file as the data source for most of today's presentation. One of the interesting things about Twitter is that it can work on more or less any device. And there was an illuminating statistic released recently that said that Twitter now is accessible by 87% of the world population. So 87% of the world population live within reach of a 3G or edge GPRS compatible cell phone tower. And if they have a cell phone capable of sending text messages, they can tweet. And to compare, to give you a comparison, only 80% of the world has access to electricity. So at this point, Twitter is more ubiquitous than electricity, believe it or not. Also, Twitter is a very rich data source, despite being only 140 characters. We'll talk about social structure, trust, and influence. And we'll mention some of this. We'll try to find some of this data today. We get a really good handle on information diffusion. How does information move through the world? We actually have a pretty good handle from Twitter on emergent semantics and emergence of languages. And how do languages propagate through the world? So very interesting things that can be mined out of huge stream of 140 character messages. Frankly, I tend to be pretty much down on Twitter followers. Not that you shouldn't follow me on Twitter, you know. In fact, you should all follow me on Twitter because you're going to find a whole bunch of interesting things. And my Twitter ID is Maksim2042. I will put it in here. So I just shared the URL with you for my Twitter account. And the reason you should follow me is I post all kinds of cool stuff related to social network analysis. But what I find is that follower relationships on Twitter have very low potential for emotional engagement. And that's where trust comes from, and that's where influence comes from. Emotional engagement is the currency of real-world social networks. You know, think about the strength of your relationships to your family, to your friends, and compare that to strength of your relationship to your Twitter followers. And that's about all we can say about it. Two-way Twitter relationships, when I follow you and you follow me, are a little bit better. They're a little bit more predictive of real interpersonal relationships. And at the same time, we have a problem harvesting this kind of data. Twitter puts fairly severe rate limiting on the search API. We'll talk about this in a little bit. And because of this rate limiting, we can only get sometimes 10%, sometimes even 1% of the real follower data. And that limits our ability to actually build reliable social networks. So we're not going to do that. We're not going to spend too much time on friend and follower networks. Instead, we're going to investigate real influence that comes from information diffusion. So, and that is fortunately not so much a subject to rate limiting, and we can get very nice results from that. So let me first show you the tweet. And you guys have all seen tweets. You have all tweeted. You have done all of this stuff. But I would like to point out some highlights in here. And the highlights are, first of all, the ad tags. So Alice retweeted from Bob, and Bob has retweeted from Carol, or mentioned Carol. Well, that in itself is 3 real people that are on Twitter, and the fact that Alice retweeted from Bob and Bob retweeted from Carol means that those relationships do exist, and those relationships contain some measure of influence. The fact that Carol has something to say that Bob finds important and invests 15 seconds to retweet, that is worth something. That is worth more than the follow button. So that is the first set of relationships. Second set of relationships is that between the blue hashtags. And the hashtags in itself, so they're used to mark concepts that people find important in one way or another, and to organize data. But at the same time, if you mention 2 hashtags in the same message, what that means is that you find that those 2 hashtags are somehow related. Now, if you find 2 hashtags related, and many other people find a bunch of hashtags related. So basically, when we take all of our tweet data as a corpus, as opposed to looking at one tweet at a time, we can start building understanding of what the community is like, and what are they talking about, and what is the semantic space, and all of the really interesting things that you can do. So we need to start collecting massive amounts of data. So I'm not going to spend too much time on data collection. I posted a couple pieces of code that will help you do data collection with Twitter, but you should just go online and see there's plenty of tutorials on how to harvest data. I would like to spend more time analyzing it rather than harvesting. So the first thing you need to do to collect data is you're going to need to create open OAuth tokens. The URL for that is on your screen. So dev.twitter.com/apps. You're going to need to log in. You need to create your app, and you're going to need to authorize it. And that will create a couple tokens. You can cut and paste them into your code. So I will show you a piece of. Let me turn on screen share. So on your screen, you should start when the screen share catches up. You're going to see consumer keys that I have created for this tutorial. You should create your own. You shouldn't you shouldn't be doing this using my keys. And you use that to connect to Twitter. And after you're connected, you can actually start running searches. So that is that is how you use Search API. This is using a library called Tweety, by the way. You don't have to use it. You can just use curl. There's lots of examples on how you can fetch data from Twitter. And frankly, I don't want to spend too much time on it with one exception. You are going to be limited to, depending on what level of authorization you have, either 150 or 350 queries per hour. That's what Twitter calls rate limiting. Rate limiting can be a real pain. If all you're getting is tweets and retweets, that's not too bad because you can get up to 150 tweets per request. So that's not bad at all. But if what you're trying to do is get people's profiles and get their friends and followers, suddenly for every follower, for every person, it takes a number of requests, and you're going to run out of requests very quickly. So Twitter scraping processes can take hours, can take days even. This is one of the reasons I tend to avoid them and look at what's happening on the stream as opposed to working using the Search API. The streaming API looks a little bit different. It doesn't use OpenAuth, uses username and password. So through the screen share, you should now see a piece of code in a file called collectstream. That file is also uploaded on GitHub. And by inserting by calling start stream with your username and password, you can start receiving stream data. You will need to follow or track. So those are lists. And follow lists is a list of people that you want to follow. So, for example, Obama, Sarah Palin, USA, etc. List of Twitter handles that you want to follow. Or track is a list of keywords or hashtags that you want to follow. Once you do that, you will start getting data. And using my stream listener class in the same file, you can modify that to create your own Twitter processing. So all of that is fine and dandy. I'm going to switch to slides. Back to slides here. I find that the main problem here is that we spend too much time on issues of data collection and we don't spend enough time on analysis. So no more data collection for today. What we are going to do is all analysis. Okay, so there is a question that just came through from Annie. Can you get yourself several keys and then have maybe 100 Twitter apps working in parallel to help overcome rate limiting? Good question. You can get away with it for a while. Eventually, Twitter will catch up with you. And they get pretty aggressive at banning people that they don't like. So you're going to eventually be banned. And sometimes your IP address will be banned, and sometimes all of your credentials will be banned. So, for a short-term project, or maybe for a class project for a university, you should be able to get away with it. But really, we shouldn't be biting the hand that feeds us. one further note is if you're willing to invest a fair bit of money, there is a company out there called GNIP. And I am pushing the URL to you right now. And this company sells, in no way I'm advertising them, but I have worked with them for a while. This company sells access to various sorts of Twitter data collectors. It's not cheap, but if you have the resources, you can have more data than you know what to do with. So, okay, so coming back to, yes. Okay, so no more talk about data collection. We are going to talk about the data that I am supplying to you. And the data is all based on the earthquake that happened in Washington, D.C. and across the East Coast in August. So as I mentioned, I started collecting data a few minutes after the earthquake happened. I've collected about 200 megs, 178 megs, I believe, of tweets. And then I stopped collecting because I wanted to have reasonably sized chunks of data to play with. So that data file is on GitHub, and I hope all of you that are interested have downloaded it. By the way, if you have cloned the GitHub account, the GitHub repository, you have also received quite a bit of source code that's related to my book. So what you should do is, so let's look at all of the files in here. Also, some of the images I used in the presentations are in this folder as well. So we're going to look at data.json. So this is about what it looks like, and we'll parse it in Python to show you a little bit better how this works. For those of you that have downloaded, the data file should be actually 137 megabytes, not 178. I was off. So check your file size. Okay, so off we go. So we're going to start Python. I'm using IPython for the shell, but feel free to use any other Python. And I am going to, first things first, I'm going to import JSON. So that is what we're going to use for reading the files. Your Python requirements are you need 2.6 or 2.7. The tools that we use don't support 3.0 yet. The 3.0 support is coming, but not for now. For data collection, you're going to need 3P. JSON, we are using a built-in parser. Now, the two libraries that we use for analysis are a little bit tricky. So the first one, actually, we're going to go in the reverse order. The first one is going to be matplotlib. That is a library that's used for plotting numerical data. Produces very good-looking graphs, such as those you're going to see in the rest of the presentation. Matplotlib requires NumPy and a bunch of other packages. It's somewhat of a pain to compile, but once you get it, you're going to get an incredible set of tools. So I have everything installed and set up on my side, but if you don't have Matplotlib set up, you might want to wait until this webcast is over, because it might take you half an hour or so to get this running. Once you do have this running, you should also install a package called NetworkX. And this package is part of suite that's used, SciPy suite that's used for analyzing various sorts of scientific data. It's a beautiful package. I am completely in love with it. If Drew Conway, the author of this package, is in the audience, Drew, I will buy you a beer, whiskey, drinks of your choice anytime because you have saved my life multiple times. And if any other authors of Network X are in the audience, please chime in on chat because I want to thank you as well. Anyway, so once you install Network X, you're going to be good to go, and we are going to start by loading the data. So I'm going to actually run this on screen share as opposed to using the slides. We are going to start by making our import. So we've just imported JSON, which we're going to need to read the file. We are going to import NetworkX and Matplotlib. Those are the two large packages we're going to need to do the work today. We disregard the warning message, and now we're ready to work with the data. So we are going to start by just opening the file. This is pretty normal stuff. We've all done this. I don't want to look at all the tweets yet. I'm going to look at one, because I want to talk to you about anatomy of tweet JSON structure. So I'm going to just say this: tweet equals I dot next. And so we now got one of the tweets in the JSON format. It's still pretty unreadable. We need to parse it. The way we parse it is we say this. So we remember we loaded the JSON package. We're going to say JSON dot load s load, which means load from a string tweet. And now we're going to print this. Oh, much better, much better. So this is essentially a structure consisting of Python dicts and Python lists. Those of you that know how to deal with those structures, which any Python programmer would, are going to be intimately familiar with it. So, what do we care about? Well, let's look at the user first. There is the user structure. Quite a bit of information on him. So we're going to say tweet.js user. There we go. There's all the information on the user. Quite a bit of stuff. So let's do some more pruning here. User screen name. There we go. Josh Barone. Oh, and by the way, the U here stands for Unicode. Those are Unicode strings because they can be in any language you can imagine. That's the good news. The bad news is if you work with this older software tools that require ASCII, you're going to have some pain trying to transform from one to the other. But we're going to stay in Unicode today. We're not going to do anything terribly fancy to it. So, okay, so we have the user screen name. Now we're interested in the social network links. So as I mentioned before, we have a social network link between people and between the person who tweeted and people who mentioned. So where do we find the mentions? We find them in a section called entities. So here there is one mention, and we would also find hashtags we talked about and URLs in the same place. So we're going to use the user mentions section. And here in this tweet, our user Josh Barone mentions the Daily Beast. So the way we would extract this is this. Entities, user mentions, okay, and so notice the square braces, that is a list, because you could possibly mention a lot of things. So we are going to do we're going to do a list comprehension here to just retrieve the names. So something like this. And if we had multiple names, multiple people mentioned, then we would have a list of those mentions, and we'd be able to form proper social network tags. So instead, what we're going to do is this. So we care about building this up for the entire social network. First, we're going to create a graph like this. So net.digraph, that's a directed graph, directed network built from the NetworkX package. So we're just going to initialize a blank data structure. And I'll show you how to work with this a little bit later on. And then we're going to say this. Okay. I'm cutting and pasting a piece of code. So I would like to talk you through it. So for every tweet in the file that we just opened, and that file is going to contain quite a few tweets in it. For every retweet in this file, we're going to load this into JSON structure. Well, here I'm trying to print it just for kicks. And then we're going to try to extract this. So what we're doing is we're extracting the author, just as I did before at the terminal. Then we extract in entities, and from entities we extract user mentions. Then we run through the entire user mentions. And every time we see a screen name, we add an edge. We're going to need exception handling here because occasionally tweets are malformed, or we have some problem with data collection, or something happened. So in this case, I just dump them. I don't do anything more intelligent. So off we go. This is going to take quite a while, and I'm actually going to switch to slides while it's running. So there's our piece of code that I just talked about, and I'm sorry for the bullets. The bullets were inserted not by me. The code itself, in a slightly more complex form, is included in the GitHub repository. So what we're going to get from this is what we call a retweet network. So retweet network is who passes information to whom. And this passing of information is basically how things go viral, how Twitter does information diffusion. Since we also have location data and timestamps, we can do very cool things mapping retweet data in time and space. So we can see how fast information moves through the United States. By the way, one of the things about the earthquake is the information about it moved faster than the earthquake. And I think some of you might have seen the video about it. So people that live sort of in the northern reaches of the earthquake zone, they actually had about 15 to 20 seconds of warning before the earthquake hit them. So as I mentioned, we're using the JSON structure. So this has been pre-parsed for us. And we're extracting retweets. There's our code. Good. And just as I got there, we finished processing. And by the way, if you're following along at home, it will die ungracefully. It will die with a value error, and that is because the data was cut off at the end. If you die with a value error like I did, that's fine. So I'm going back to screen share, and there we go. So let's see what we gathered. So retweets is a digraph object that we have just created. Well, how big is it? How many people have done the retweeting? Well, if the graph object is very similar to a normal Python data structure, so we can run len. We have 38,000 retweets. 38,338. And if you were so inclined, and if you were on a fast machine, you could do this. Retweets. But I am warning you right now not to press enter, because if you do, you're going to tie up your machine for quite a while. That's just 38,000 nodes is going to probably take several hours to render, and you're not going to enjoy the process. So instead, I'll just show you approximately what it looks like. So this image basically, what it shows you is that on the outer side, there's a whole bunch of pairs of nodes, single retweets. One person retweeted, and that's about it. And then in the middle, there is a few cascades. So the graph consists of many pairs of nodes, but very few connect into coherent clusters. But clusters are what we actually want. Clusters give us information about who was successful at passing information through. One retweet is not successful. Many is good. So we're going to look for those clusters, and in this case, we're looking for connected component subgraphs. For those of you that study graph theory, that's the formal name for it. And there is the code for doing this. By the way, the commands I'm typing in, they're also available. They're not. The main code is in webcast.py, and the commands are in command.py. So everything that I type here, I'm actually cutting and pasting from here. So first thing we're going to need to do is we're going to need to transform our directed graph into an undirected. So I'm going back to screen share. there's the command. So retweets, which is our graph structure, dot to undirected. Takes a couple seconds. And then we do second step is we find the connected component subgraphs. So that's also a built-in function of NetworkX, which is one of the reasons I love this package. It's fast. So what is comps? Components. Well, it's lots of graphs. Well, but every component actually consists of a couple nodes, two or more nodes connected by an edge to their graph. And we have isolated little subgraphs that are disconnected from each other. Now, how many of them are there? 10,000. There's 10,000. So 10,000 little subgraphs have come out of this whole thing. If you think about it, most of those are going to be tiny, and then there's going to be a few larger components. So let's find out. So I'm going to use another. We're going to use len as a way to compute the size of a graph. And the graph is going to be one of the components. And we're going to use a list comprehension to do this all in one line. Something like this. So as you see, most of the components are size 1 or 2. But I want to do something a little more rigorous. So I'm going to use matplotlib, our plotting library, to create a histogram. And we do this by doing this plot.hist of sizes. And I'm going to use probably 50 buckets. And here comes the histogram. So you see there's a lot of components that are tiny, and then there's one or two that are huge, going up to the 10,000 nodes range. So one of the useful things about the components function is it produces them in sorted order. So component 0 is the largest. It's nearly 10,000. And that one we can actually draw in a reasonable amount of time, which, again, I'm not going to do here because I have already drawn it. I don't want to spend the time doing it. So instead, I'm just going to show you this way. There's the command. So retweets, which is our graph structure, dot to undirected. Takes a couple seconds. And then we do second step is we find the connected component subgraphs. So that's also a built-in function of NetworkX, which is one of the reasons I love this package. It's fast. So what is comps? Components. Well, it's lots of graphs. Well, but every component actually consists of a couple nodes, two or more nodes connected by an edge to their graph. And we have isolated little subgraphs that are disconnected from each other. Now, how many of them are there? 10,000. There's 10,000, so 10,000 little subgraphs have come out of this whole thing. If you think about it, most of those are going to be tiny, and then there's going to be a few larger components. So let's find out. So I'm going to use another. We're going to use len as a way to compute the size of a graph. And the graph is going to be one of the components. And we're going to use a list comprehension to do this all in one line, something like this. So as you see, most of the components are size 1 or 2. But I want to do something a little more rigorous. So I'm going to use matplotlib, our plotting library, to create a histogram. And we do this by doing this plot.hist of sizes. And I'm going to use probably 50 buckets. And here comes the histogram. So you see there's a lot of components that are tiny, and then there's 1 or 2 that are huge, going up to the 10,000 node range. So one of the useful things about the components function is it produces them in sorted order. So component 0 is the largest. It's nearly 10,000. And that one we can actually draw in a reasonable amount of time, which, again, I'm not going to do here because I have already drawn it. I don't want to spend the time doing it. So instead, I'm just going to show you this way. So the largest connected component looks something like the one on the top, but there's a lot more nodes on it. And the next largest is actually quite a bit smaller. It's only 100 and some nodes. So each one of those connected components corresponds to an information cascade. So every time something goes viral, every time something has serious amounts of diffusion to it, is going to be an information cascade. So we need to figure out who causes the biggest cascades. In this case, the easiest thing to do is to calculate degree centrality. That's a social network metric that I described in the book in quite a bit of detail. And degree centrality is simply number of connections emanating from a node. So high degree nodes have caused the most retweets in this particular case. Also, we can drop low degree nodes. So here's what we're going to do. I'm going to say degrees equals net.degree, and it will produce a Python dict person's name and followed by his degree. The degree distribution, if we histogram it the exact same way we histogram the size of subgraphs, is the same way. So we have a lot of people with degree of 1 and a couple with very large degree. So to help us find the core, I created a function called trim degrees. This function is available in the webcast.py. And trim degrees basically removes nodes with degree of 1, or, well, you can set the parameter. And when you do that, when you run this function, if you look at the end of this slide, you're going to see core. So we create a core graph by running trim degrees on this largest component. and we lose about two-thirds of the graph. And at the end, it looks like this. So we have a few dense subcenters and the periphery. So now we need to find out who are at the center, who are the centers, who cause the most dense retweets. So for that, I've created a little function that sorts degrees, so you can cut and paste that into your Python environment. And one of my gripes for the degree function is it returns an unsorted list. So it's not easy to you have to jump through a couple hoops to find who has top 10 degrees. Well, I jump through those hoops for you. You can cut and paste it from my code. What you get is this: the top people who cause the most retweets. Interestingly enough, it's a mixture of celebrities, news sites, and sort of everyday people. So Kevin Hart for real is the actor, Kevin Hart. Lord Voldemort 7 is virtually unknown blogger. Breaking News is a real honest-to-God news site, CNN Breaking News. Darth Vader is somebody, I'm not actually sure who this person is for real. Katz is a digital journalist. Then we have another news site, AP News, followed by Diggy Simmons, the rapper, and a couple other guys who are bloggers with not very huge reputations. So here's the interesting thing. We are isolating retweet network as it's happening, during the event as it's happening. And we see that the power of an individual being in the right place in the right time and being connected into a cluster is very important. Lord Voldemort 7 has higher importance in this particular case than CNN. And that is one of the places where Twitter has the most power for information diffusion. I've showed pictures in the past, and you can find them on my website, of people having an immense amount of power during the Egyptian Revolution. People that had fairly little clout. You know, if you use clout with a K, or people who had fairly little connectivity, but yet they were in the right place in the right time, and they made a difference. So now we know who is talking. Next step, what are they talking about? And so what we're going to do is we're going to use the humble hashtag. Hashtags are spontaneous, relatively spontaneous. And when two hashtags are used together in a tweet, we can presume that they're somehow related, and that the person did this intentionally. Now, occasionally we get people using a ton of hashtags at the same time, and more often than not, those are spammers. So you'll see there is actually a pretty easy way to isolate spam on Twitter just by using hashtag analysis. So we're going to collect a hashtag network. This time, this is going to be a valued graph. So what we're going to do is every time a pair of hashtags co-occurs in the same tweet, we're going to increment the counter. And this counter is going to be basically a graph structure, just like the one we used for collecting retweets. When two hashtags co-occur many times together, that signals that there is some kind of a real semantic connection between them. And the more often they co-occur, the more real this connection is likely to be. So if two hashtags happen to co-occur only once, we can safely throw them away. If it's thousands of times out of 30,000 messages, well, something is important there. So here's a helper function that you're going to need to add. So this function creates counter edges. Every time you add an edge, it increments a counter. So you're just going to have to cut and paste this one as well. And this is included in the webcast.py. So those of you that are following along this, your Python interpreter, just grab that function. So we're enhancing the code here. So we create another graph for hashtags, hashtag_net. That's on line 2. And we're going to also start collecting hashtags. So that we use this code here to gather hashtags. And look at lines 2, 3, 4, 5. Basically what I do is I go through the list of hashtags and I create an association with every pair of hashtags that unless they're the same. So that is basically so we get clusters of hashtags when they're used together. When you use 3 or more, I want all of them connected together. So as a result, we get okay, so as a result, we get hashtag network with about 1,700 nodes, 1,700 hashtags involved in it. We can directly draw it, and that's what it's going to look like. That's actually a very familiar view that you get. There's a central cluster in the middle, and a whole bunch of disconnected pairs on the outside. So we're going to zoom in on the central cluster. That's where the interesting things are. And we use the exact same thing, connected component subgraphs, exact same technology that we used last time. And then I'm going to do one more thing. So the central topic here is earthquake. Everybody knows this is all about the earthquake. But I care about what do people talk about in connection to the earthquake. So what I'm going to do is I'm just going to delete the central topic. So if you drop the word earthquake from this graph and replot it, we're going to get we're going to get a semantic network of other topics linked to the earthquake. And if you start studying this, you're going to see the obvious connections with newscasts. You're going to see obvious connections with celebrities. You're going to see obvious connections with safety warnings. But then you're going to see a whole bunch of unobvious things. And to get to those, we're going to go to the valued network. And what we're going to do is we will drop associations that are not highly prominent. We're going to drop everything at this point with weight of less than 2. So that gives us still somewhat of a hairball cluster. And then but then I'm going to drop everything with weight of less than 10. So we've now zoomed in on the real, the cluster on the left is the real cluster of meaning, the high grade meaningful data. And then on the right is the small clusters that represent spammers. By the way, spammers will always float to the top. This is very easy to detect and very easy to remove because spammers all look alike in this particular analysis. So basically what I'm showing you is that you can take this network and you can use this core when you're done trimming away all of the fat. You can use this core to write a taxonomy of the event. So what did people talk about? What concepts did they use? What concepts were related? You can actually give this to an ontologist, and it will make remarkably a lot of sense. This is what you would call folksonomy. So a taxonomy or an ontology that emerges from the world natively. And really this is what I would call poor man's latent semantic analysis. Latent semantic analysis being a very serious statistical technique. You can do it much quicker using network analysis. Anyway, much more, this and much more. You can find how to do this in my book. I just gave you a very quick survey of what can be done with Twitter data and where you can take this. You can follow along with all of the exercises in the book. As I mentioned before, the book is 50% off today, just for 1 day. And I hope you enjoyed the webcast. I hope you enjoyed this deep dive. And if you have any more questions, I will be happy to take them.